Have you ever really thought about what makes a baseball fly through the air, or what pushes you back in your seat when a car takes off? It all boils down to a few incredibly elegant rules figured out centuries ago. Today, we're going to crack open the code on Newton's laws, the literal blueprint for how pretty much everything in our universe moves.
So, let's start with the most basic question of all. What actually makes the world move? It sounds huge, right? But the answer is surprisingly simple. It's not some cosmic mystery. Instead, it all comes down to one key player, the absolute star of this whole show.
And that star of the show is, of course, force. Before we can even get into Newton's famous laws, we've got to understand what a force actually is. Where does it come from? What does it do? We've got to get to know its anatomy.
Okay, so here's the first big idea. A force isn't something an object just has. It's not a property like color or weight. A force is an interaction. Think of it like a conversation between two objects. You need a source doing the pushing or pulling, and a receiver that gets pushed or pulled. If you don't have both, you don't have a force. Simple as that.
Now these interactions, these forces, they come in two main flavors. First, you've got your contact forces. These are the obvious ones that require things to actually touch, like friction, or the tension in a rope, or just the floor holding you up right now. But then you get the really weird ones, the non-contact forces, things like gravity or magnetism that can reach out across totally empty space and still have an effect. Kind of spooky, right?
So now that we've been properly introduced to our main character, Force, it's time to learn the rules of the game. And those rules are Newton's 3 fundamental laws.
The first law is a huge myth buster. A lot of us intuitively think that to keep something moving, you have to keep pushing it. Newton says, nope. An object in motion is perfectly happy to stay in motion, coasting in a straight line forever, just like a spaceship in deep space. You only need a net force to change what it's doing, to speed it up, slow it down, or make it turn. That stubbornness, that resistance to change, is what we call inertia.
And that brings us to the engine of it all, the second law. This is the famous F equals ma. It's the recipe that tells you exactly how much an object's motion will change. You can see it right here. You give that 20 Newton push to a bigger, more massive object, and you get way less acceleration. Why? Because mass is just a measure of that inertia we were just talking about. More mass means more stubbornness.
And finally, the third law, which reveals this beautiful, deep symmetry in the universe. Forces are never lonely. They always come in pairs. When this jumper pushes down on the ground, that's the action. But the ground pushes back up on the jumper with a force that's exactly equal and opposite. And that reaction is what actually launches them into the air.
Okay, wait a minute. This leads to a question that trips almost everyone up. If for every action there's an equal and opposite reaction, shouldn't they just cancel each other out? How can anything ever move if every single push is met with an equal and opposite push back?
And here is the secret. It's so important. Those action-reaction forces act on different objects. The book pushes down on the table, and the table pushes up on the book. To figure out if the book is going to move, you only care about the forces acting on the book. The force pair can never, ever cancel out because they aren't acting on the same thing. Getting this one idea straight is a total game changer.
So to make sure we don't fall into that cancellation trap, physicists have an incredibly powerful tool. You can think of it like a special lens, a pair of glasses that lets us see the world of forces with absolute clarity. It's called the free body diagram.
A free body diagram, or FBD, does one simple vital thing. It isolates a single object from everything else around it and just shows us the forces acting on that object. The golden rule here is you never ever include the forces that the object is exerting on other things. This is how we focus on what matters and apply Newton's laws correctly. And making one is actually a really simple process. You start by just representing your object as a dot. That's step one. Easy. Then you start adding forces. Gravity is almost always there pulling straight down. If your object is sitting on a surface, that surface pushes back up. That's called the normal force. And finally, you add in any other pushes, pulls, or friction that might be in the picture. That's it. It's clean, it's simple, and it is unbelievably powerful.
All right, we have the laws, and we have the tool. Now it's time for the payoff. Let's put it all together and see how these ideas create this amazing step-by-step pipeline for solving basically any problem in mechanics.
And here it is. This 6-step process is the algorithm. And just look at what's right there at the top. Step 1. Draw the FBD. It is not a suggestion. It is non-negotiable. Starting with that diagram is the foundation for everything else that's about to happen.
This is where it all just clicks into place. You might have a problem that looks messy, with a force coming in at some weird angle. But all you do is you break that force down into its basic pieces. You ask how much of this is pushing sideways and how much is pulling up. Once you've split it into these simple x and y components, the problem becomes so much easier. You can find the total force in each direction, and then, using F equals ma, you find the final acceleration. It's a beautiful, systematic approach.
So let's just zoom out for a second and take a look at the big picture, bringing all these different pieces together.
Let's look at all three laws side by side. The first law? That's the condition for staying the same, no change. The second law, that's the math of change. It's the engine. And the third law? It describes the nature of the forces themselves, that they're always a two-way street. Three laws that together create one totally unified system.
And this chart right here, this is the entire workflow. It all begins with the physical interaction between objects. That interaction creates forces. We then use a free body diagram to isolate and visualize those forces. And that diagram is the key that unlocks our ability to apply Newton's laws and actually predict the motion. It's just an elegant and powerful process.
You know, the formulas are important, of course, but the real deep understanding comes from the visualization. So if you take away just one thing from all this, let it be this: master the diagram and you will master the mechanics.